before I kind of divulge into energy carriers, I want you to just keep in mind the concept that we talked about earlier about how oxidation reactions are always going to release energy. And we did kind of talk about this when we went over the fatty acid tails or free fatty acids of, and also the fatty acid tails, I guess you think of it, of the phospholipid bilayer. And in this context, this energy that's released from an oxidation reaction, this can be in the form of, say, like a combustion, or this can be in the form of high energy electrons, right? Energy is energy. The medium behind it doesn't really matter. But what's important is that you understand what makes something combustible also with what makes something able to give off a lot of energy, and that is how reduced the compound would be. So just thinking about here, and I think we've already talked about this in I think a later video, but which is going to give off energy more, methane or say, you know, CO2, right? Well, if I give off methane and I expose that to a fire, it's going to cause an explosion, whereas CO2 is not going to cause an explosion. And by the same notion, if I were to compare that with, say, methanol, that's going to give off a little bit less energy than methane was, but it's still going to be combustible and it's still going to give off a lot of energy as opposed to, say, say a methane group attached to a carboxylic acid, all right? So the amount of however reduced something is, that determines how much energy it's going to release upon oxidation. And in this context, rather than saying combustion, we're going to talk about the amount of energy that's giving off in the form of high energy electrons. So we have two electron carriers that we're going to talk about. And these are the ones that are pyridine nucleotides and then the flavin. So for the pyridine nucleotides, there's really just, I'm only going to draw the structure of one, but you can imagine the variable of what's the differences between the two. These have really unique structures. Notice that these are all derived from B vitamins. So for the structure we have NAD+, and this is, I'm going to draw it in the oxidized state, and then I'm going to include NADH, which is the reduced state. So in the oxidized state, NAD+ looks like this. So it's the positive formal charge that you're going to see at the ring of the nitrogen. That's what the plus is in the NAD+, right? And so it doesn't really react with a hydride nucleophile, but the way that I just envision it is that it's like as if it did, hypothetically speaking, react with a hydride nucleophile. And so let's draw it like this, saying that we're reacting with a hydride nucleophile and also a proton that's arguably dissolved in acids, like hydronium. So this is what it looks like in the reduced form. I'm not done drawing it yet. The identity of the R group really doesn't change much from this to this, but I guess, let me see if I can color coordinate this. I don't know if that makes it worse or better, but anyways, that's the hydrogen, that hydride, quote-unquote, the quote-unquote hydride nucleophile that I just drew there, that it doesn't exist in that. I'm just using that for pedagogical purposes to think about the two electrons being in that form. That's the way that they react. They bind to the topmost part of the ring, and this hydrogen protons that we get in the acidic concentration that's probably dissolved with hydronium, assuming that it's water, hasn't really changed much either. And so that's the differences between the oxidized and the reduced forms of NADH. One of the things that I didn't quite mention that I'm sure you're able to somewhat observe, and it's not really present because of what's happening to here so much as if we were to show the identity of the reactants of this, but usually the mechanism for pyridine nucleotides, the mechanism that it has of oxidation is to increase the carbon-oxygen bonds of the reactants that it activates. And my textbook, for whatever reason, and I don't quite understand why, really stresses a Gen Chem definition of oxidation and reduction of, you know, Leo the Lion goes grr. But I always prefer to use the organic chemistry definition of oxidation and reduction, and that is if you're increasing the amount of carbon-oxygen bonds, you're having oxidation. If you're decreasing the amount of carbon-hydrogen bonds, you're having oxidation. And by the same notion, you're having reduction if you're increasing the amount of carbon-hydrogen bonds and decreasing the amount of carbon-oxygen bonds, right? The difficulty of this textbook is that they keep things abstract without giving specific examples, which is nice for an overview and it's nice for textbooks and it's nice for videos, but at the same time, whenever I'm learning stuff, I like to see specific examples given. That's just the way that I am. So for the functions of this, there's really just two functions that are involved in this. One of them, in case you don't remember from high school or general biology, would be ATP synthesis. Right? Remember, it goes and plays a role in oxidative phosphorylation. And the other thing that it does is it plays a role in catabolism. Now, not NAD+, but his phosphorylated cousin, NADP. Go ahead and draw them in the reduced form of NADPH. So the differences between these two molecules, between NAD and NADP, is just the identity of the R group, which this is not a majors class, so I'm not going to really stress that so much. But if you were to actually look at it, if you were interested for whatever reason, the extra phosphate group that's being there, where there would be at the 2' hydroxyl group, we now have that esterified with the phosphate. So esterified with, and this right here, this esterification site that we've happened on the R group here, this is a site for enzyme binding. What type of enzymes? Well, catabolic enzymes. Enzymes that are designed to build things, to synthesize things. If you don't remember from your high school or general biology class, when we talked about the Calvin cycle, we talked about using NADPH to go ahead and start to create complex 6-carbon molecules. And so that's where that comes from. The next one would be the flavins. And really, both of these guys and the pyridine nucleotides, they're doing the same thing, right? They're both playing a role in ATP synthesis. And just to keep it on just even terms here, which we talked about catabolism here, ATP synthesis, is an anabolic reaction or an anabolic process. How is this accomplished? Or what is, I guess, the overall role that they play in ATP synthesis? Well, that's the role that they play of electron transport, which is why the name that they're given. What do I mean by, or why are they good at doing their jobs of electron transport, might you ask? Well, that's because they have a higher affinity for electrons than the carbon compounds that we oxidize. A higher affinity than the carbon compounds that we had oxidized, and by the same notion, it has a lower affinity than O2 itself. A lower electron affinity than oxygen. I know I'm running out of room there, but anyways, this is a generalized mechanism of how these guys work to play a role in oxidative phosphorylation, which gives us ultimately ATP, right? So now let's talk about their structure. And just like before, how I mentioned in this one, the reaction of the pyridine nucleotides is to increase the carbon-oxygen bonds. The general reaction in this context is to, you can think of it as increasing carbon-carbon double bonds or decreasing carbon-hydrogen bonds, right? Either one of those are kind of the same thing, but that's the general mechanism for that. Okay, so that's what FAD, not FAD+, just FAD looks like in the oxidized state. And I have got to find a better way to draw my compounds. I'm having flashbacks of the OChem videos I had to make. But the way that I look at with the FAD type of reaction is that FAD is going to react with, and no, this is not, again, a direct mechanism. So the way that I envision these reactions happening is if we could imagine a hydride 2 hydrogen like radicals, and imagine them kind of pulling the electrons out from the NH, from the nitrogen double bonds here that I'm kind of trying to underline with my pen here. Those are going to be the ones that are going to take part in this reaction that's going to ultimately result in its reduction. So this is the oxidized form of FAD. Now let's draw the reduced form, which would be FADH2. So if you could just kind of imagine dragging these things out here and adding hydrogens to them across that format there. One of the things that's interesting to me about this is that this is a reaction that, to the extent of my knowledge, whenever I sit down and draw this, is the effects that this has of aromaticity and how this plays a role in how our bodies can work around the effects that this is going to have on aromaticity.